So there was a good question asked about axiom 2, which is the axiom of regularity, and what it really says. And it's stated, like all the other axioms, they're stated in a very general way, and these phrases were created with lots of thought. And again, the idea was you want to make a list of axioms which is somewhat small as possible, so that the axioms are independent in the sense that none of the axioms can be actually proven by the other ones. So in a sense, you need them all to have a useful set theory and logic. But you also don't want to have too few axioms, because if you have too few axioms, then you really can't prove any theorems, and you can't really make any conclusions about our world or our universe. So the question was related to axiom 2, and the main point, as I put it in the notes, is that axiom 2, or the axiom of regularity, is one of the things that helps us prevent Russell's paradox. Now, if you recall, Russell's paradox is the problem of actually defining the concept of a set as a collection of elements, or a collection of well-defined objects. The whole point of an axiomatic set theory is to avoid this and other kinds of paradoxes, because you really can't define the concept of what a set is with a specific definition. What you have to have is a list of axioms which every set must not violate. So in a sense, sets are kind of defined in some weak sense. As long as you have a collection of well-defined things which happens to not contradict any of the axioms, then that set actually is a set. So the idea is to prevent Russell's paradox when you're constructing a useful set theory. So the idea is, let's assume the axioms of our set theory, or ZFC, are all true. That's what we do when we're doing mathematics. And again, the axiom of choice here is not really important. It really won't play any role. And in fact, we don't need all of the axioms to get to this contradiction that we're going to see, but let's just assume all the axioms are true. Then what's the idea? We want to prevent the existence of a set, X, which contains itself as an element. All right, remember, a set is always a subset of itself, but a subset's not the same thing as an element. A subset is a set of elements inside of a set, but an element is a particular element inside of the set. So we imagine that what happens if there is a set X where X is one of its elements. We want to see how this is prevented by the axioms of our set theory. See basically how this will lead to a logical contradiction of our axioms that we're assuming to be true. So a couple axioms we use right away. The axiom of the power set, let's recall what this is telling us that the power set of X is actually a set. And this is an assumption that we just have to have. We want to make sure that once we have a well-defined set, creating the set containing all of the subsets of a set actually does exist as a set. And again, we denote this by this P of X. So this is a set. Next, we refer to the axiom of schema specification, which is basically just saying that once you have a well-defined criteria and a bunch of well-defined objects, you can always group some of those objects into a set, provided they all satisfy this condition. So how we're going to define a subset of the power set of X. So what it's going to be is a collection of some of the subsets of X. So we're going to call it B for bad. This is going to be our bad set, which is going to lead to our contradiction. So, and again, I use the colon here to just say we're defining the symbol B. So again, what is it? It's the set of all things in the power set of X, such that X itself is an element of that subset. So again, in words, it's just the set of all subsets of X which contain X as an element. Since X contains itself as an element, such subsets do exist. Let's take a really simple example. Let's suppose there exists a set whose only two elements are itself and the number 1. Then the power set has there are four subsets of this set. There's the empty subset. There's the set containing the first element, which happens to be X, but we have to write that with brackets. The set containing X is a subset of X. The set containing the other element, 1, is a subset of X. And the set X itself is a subset, because a set is always a subset of itself. So in this example, let's just notice what this means. What is B? B is just the set of these things which contain X as an element. Well, this set contains X as an element. But as we've done from the beginning, we're assuming that X contains itself as an element, because X is really, we're viewing it as some set containing X and some other things. And in this case, it's just X and 1. But in general, this example is just a way to visualize it in a simpler manner. This argument is working for any such X if we define such set. So B is just, in this our example, has two elements. It has the set containing X and the set X itself. All right. So let's notice something about this set B. If I take any element of B, then when I intersect it with the set B itself, it actually contains something. It's not empty. All right? No matter which element of B we choose. Let's just look at it. If I take this set, the set containing X, and I intersect it with B, well, this set contains X as an element, and B contains X as an element, so the intersection would not be empty. Now what if I take another element, the other element, X? If I take X and intersect it with B, I get X, because X itself, remember, X itself actually contains itself. This is the kind of circular logic we're trying to avoid. So what do we have? Regardless of this example, so this example is just helping us see it much more easily. If I have a bad set, X, that contains itself as an element, then we can always define this set B, which basically contains all the subsets of X which happen to contain X as an element. All right? This is a non-empty set, as our example illustrates for us. And what is the property of this set? Every single element of B has a non-empty intersection with B. All right, so this is the problem. The axiom of regularity, as stated in our notes, says for a non-empty set X, there exists X and X so that X and little x and capital X have no common elements. Well, this is confusing because capital X in our specific problem here is a specific set. This statement of axiom of regularity is in general. So let's rewrite it. So all we're going to do is we're going to rewrite it, and we're going to, instead of putting in capital X and little x, we're going to put capital B and S as an element. So the statement's exactly the same, but now it actually is useful to us. So what did we do? We assumed there exists a set X, which contains itself as an element. We used a couple of the other axioms of our ZFC set of axioms to prove that some set B exists, which is non-empty, and has this property that when I overlap B with any of its elements, which are all sets, I get a non-empty overlap, or a non-empty intersection. What the axiom of regularity says, the only thing that's allowed to be a set is something that is if it's a set B, or X, or whatever you want to call it, such that there has to exist some element in B such that S and B have no common elements. So by assuming this horrible set X exists, which has itself as an element, allowed us to use the axioms of ZFC to construct this set B, which fails axiom of regularity. Therefore, our base assumption must have been wrong, and our base assumption was that capital X was a set. So this is how we prove that the axioms are set up in a way to prevent us from considering sets that contain themselves as an element. And therefore, Russell's paradox doesn't exist if you stick to the assumptions of the axioms and use logic only based on the validity of those axioms.